So, what is TorchVision Models and what it's all about? So, here we're going to discuss how to use the pre-trained computer vision models like ResNet 50. We're going to use the TorchVision models, running image classification, understanding outputs like from logits to probabilities to the labels, preparing inputs correctly, and getting class names. So, why pre-trained models? Instead of training from scratch, uh, we could use the models already trained on the huge datasets like ImageNet. By the way, ImageNet consists of thousands of classes. What is powerful? It saves time. It needs less data. Already learned useful features like edges, shapes, and objects. This is called train transfer learning or um, fine tuning. If you want to train some of the parts of the the neural networks layers, especially if the pre-trained model um, doesn't or does not trained into a particular rare um, um, data that it needed to predict. So here are the popular architectures um, like VGG, ResNet, and GoogleNet. These are different neural networks designs for images. Example, ResNet 50 consists of 50 layers, or what I call 50 layers deep. Um, it's very strong for classification because as the more layers, the more patterns uh, it could learn. But there is must be there's something that we must thinking about um, when we architect or building the architecture of the neural networks. So here's the step-by-step pipeline. First, we load the model or the pre-trained model. Like in the PyTorch, we call it ResNet 50, and we set it's a pre-trained is equivalent to true. It means it will load the weights trained on ImageNet. The key idea here is we are not starting from zero. Next is to set to evaluation mode. This disables training behavior like dropout, meaning we are using this model to predict the unseen data or for prediction and not training it. So the weights or the parameters are already fixed, and we are not intended to update those parameters or the trained weights, trained patterns. So we prepare the input image. The model expects like the size of 224 by 224 pixels. We normalize values, um, specific mean, and standard deviation. And pre-processing steps. Resize, we center crop, we convert the tensor, and we normalize it. Why? Because the model was trained that way. So the important rule here is input must match in the training format. Next is we add the batch dimensions like image that increase to zero. It turns the shape uh, from having these channels within height to batch size of the batch um, channel within height. Why? The model expects a batch, even if only one image. Next is we run the inference. So we expected the outputs. That's why we fed the image into the model, and the output we call it logits. So what are logits? These are raw scores for each class. Like for example, in the image that is a thousand classes, and each those thousand classes output produce the raw scores like 2.3, negative 2.2, 1.2, 5.6, and so on, so forth. So the important key here is this is the probabilities. It can be negative and it's not normalized. And then we convert those logits or raw scores to the probabilities using the softmax. So the softmax equation is the natural log or raised to the z sub I divided by the summation of uh, um, natural log or natural number z raised to the uh, z sub j. So now the values are now between 0 and 1, and the sum is equivalent to 1, meaning how confident the model is. So we get the top predictions. Like for example, we get the top 5 class indices uh, using the torque.top k and their probabilities, and we convert those top 5 uh, from the converted index to the class name. Like for example, the model outputs 207, and but we want the class name or the labels of it. If we want the golden retriever, like for example, we need a mapping file like JSON. Example, 137 means in the label index, it's golden retriever. So there's a two ways to get the class names. The old way or the manually, we use the download. We need to download the JSON mapping and look up of indices. But the problem is we need the external file needed. Here now in modern way, much better. We use the weights metadata. The model stores the model stores those class names, the number of classes. So the advantage of having the class names in the model and the number of classes is we need no manually to look up, and it's much so cleaner. So let's look about the deep laboratory or the segmentation. So the different task is segmentation or the pixel level classification. Um, say, let's say we have the model deep lab 3 plus ResNet 50. Those have different architecture. It detects 21 classes and not 1000. So example class is dog. So here's the concept that we must understand. A model is like a function. It has a relationship between the input and the output. So some of the parameters or the trained weights are expected the pattern. So what you input produces um, certain um, pattern. Okay, so the flow is from image to the model, and the model um, produces the logits or the raw scores, and we convert it to probabilities from 0 to 1 and sum up to 1. And the one who has or had a large amount of probability um, is the one is the answer. By the way, we must convert it to label after we turn it to probabilities. So we must keep in mind the pre-trained model already knows the edges, shapes, and objects or the patterns. So we so we could reuse those knowledge. Next is input consistency. If we don't preprocess correctly, model performance drops badly. Next is logits versus probabilities. Logits is raw scores, while their probabilities is confidence. Next is class mapping is required. Model doesn't output dog, it outputs number, like 107, and we must translate it. So here's a summary. We could think um, uh, pre-trained model is already studied on 1,000 objects. Image is like a exam questions, and logit is raw guesses, and softmax is confidence level, and JSON is the answer key or the labels. So TorchVision provides pre-trained models. Models trained on ImageNet or 1,000 classes, and there's a lot of models or pre-trained models out there, but ImageNet provides the general patterns that that um, trained on its own architecture. So we load the model, we prepare the input, we run the inference, we get the logits and convert the probabilities and map the labels.